Hey, okay, welcome. Here we are at day 3, and this will be our second lab. And so let me begin like I did the first lab and say today's lab has to do with the material from today's lecture. So if you haven't already seen today's lecture, you don't have to necessarily do the homework, but watch the lecture first and maybe even read the book, because what you hopefully will get across in there, many things, but as we're working with Newton's laws, there's a part in there where I talk about what's a vector. And I want you to kind of get a better feel for vectors. And that's what today's lab is. Today's lab is a little experiment to give you some indication on how to work with vectors. And it's also kind of a verification that when we draw these little pictures, that again, if you saw the lecture, and so let me just say, if you haven't seen the lecture, hit pause right now, hit that space bar, and then go and watch that lecture. And in that lecture, you'll have seen me talk about the difference between a vector and a scalar and what a vector is. And a vector then is any quantity that has a magnitude as well as a direction. And I keep emphasizing throughout the lecture how important it is to consider not just the magnitude of it, but also the direction of it. And that's what today is, because we're going to be working with forces. In fact, in the lecture, assuming you already watched it, you will see I listed 4 vectors. That's not all the ones we'll cover this semester, but those are the 4 we've done already. And one of those is forces, and that's what we're going to do in this lab today. Another one is distance or position, and so we're going to kind of use that one. See, what we're going to do is we're going to draw things, and so distances will be our vector, and then we'll translate the result of using distance vectors to see how that also gives us the same and accurate prediction if we use force vectors. So take your lab manual if you haven't already and open to page 14. And so I've got my lab manual here. Let me encourage you to read the first part of 14 where it talks a little bit about vectors, and then it gets into the procedure. And you can read that if you want, but the truth is I'm going to lead you through the procedure. And so this new online environment is kind of a new experiment for both me and for you. And so as I said in our first one, I'm going to pretend like I'm your lab partner. And so we're just going to work through the lab, and some of the things I will do and you'll write down, and some of the things I'll leave for you to do, and just like you were working with your partner. And so I'm going to turn the page, and that gives me 15. That's the rest of the procedure. But the main page I want to hold up and have you look at here is page 16. And page 16 has this little it kind of looks like a table. It doesn't have lines in it, but it's a table that lists 5 different sets of forces. And I say set because there's 2 forces for each line, each set. And what we're going to do is we're going to add those forces together. So we're going to do really kind of the same thing 5 times. We're going to add 2 forces together. And that's called the net force. And we're going to see what those add up to. And we're hopefully going to see some patterns develop. And then you have 3 discussion questions that you will answer. And I might help you with those discussion questions because they're really good questions, but they're terribly written questions. And so a lot of times students read them and they're not real sure what they're saying. And so if this was face-to-face, I would just kind of leave you at that and walk around the room, and inevitably half of you will ask me, what's the author trying to say? Since we're not face-to-face or remotely, and I know that, I just want to clarify these questions and maybe even partly answer them. I don't want to do too much of the work for you because I do want the learning to go on here, but give this some thought, but I don't want to leave you hanging. In any case, like I said, we're going to do some drawings, and in a face-to-face setting, I would give you a protractor. And we've got 2 different models. Actually, we got more than 2. This is just 2 that I grabbed. Doesn't really matter, but if you have access to a protractor, that's probably best. Get yourself a protractor. If you don't, let me give you an option here, but just a second. Another thing you'll need is a straight edge ruler. that one I'm going to assume you do have access to. And so find yourself a ruler somewhere. What you'll need really is the straight edge and then the markings in centimeters. That's the big thing here. So find yourself a ruler. The third thing you'll need at home here is some graph paper, which again you may or may not have access to the graph paper. So I'll give you some idea if you don't. And here's that idea. Let me turn on the computer here. I'll turn this on. And what I did here is I just Googled printable graph paper. Whoops. My machine just went to sleep. And so before I started this recording, or actually last night just to see if it was possible, I go, how am I going to get the students graph paper? And so I just, in the Google window, typed in printable graph paper, and all these great images came up. And it doesn't really matter what ones you get. I'll just, this one showed up first, so let me print on it, or let me click on it, and it's got the image here. And so anyways, it has right there, free online graph paper. So again, just kind of make your own graph paper. Most of this is to get the idea anyways, and so if you don't have the most accurate graph paper, that doesn't really matter. And the spacing between the squares on the graph, again, doesn't really matter here, because we'll do the distances with the ruler anyways here, okay? So that's the idea. The other thing that you might want to Google, and so I'll just go printable protractor. Actually, we got downloadable one. I don't know which is better to Google. But go ahead and download one of these and print it. And of course, cut it out. You don't have to cut out the middle. And unfortunately, it wouldn't be see-through, so you're going to have a little bit more of a challenge, but we'll just make sure we draw the lines long enough for you that you can do it. But you need to do that first. And so I'll say, you know, hit the pause button right now and go ahead and print these up and get yourself so that you have all three of these. Graph paper, a straight edge that you can measure in centimeters, and a protractor, whether it be a full circle or a half circle, doesn't really matter, just something you can measure angles. And also, if it's been a while since you've used a protractor, go ahead and go to YouTube and Google how to use a protractor. For some of you, it probably has been since 5th grade since you've worked with a protractor. I know in a regular face-to-face setting, with a class of 15 groups, there's always 2 or 3 who go, "Ooh, I don't remember how to center up a protractor." So go ahead and Google that. There were some really good ones there, or if you need any help, I'll send you the links to the ones I've Googled, or even I'll make a video myself and show you how to use a protractor. But let me turn this off because I know it messes up the lighting here. And so power down and get this out of the way. And say, all right, now let's start the lab. And so on this lab here, and I'll just kind of put it here on the board, your first experiment says do this. Take a weight that is 100 grams at 0 degrees. Force number 1. And take another force, which is 100 grams at 120 degrees. Let's call this force number 2. And so we're going to see what do you get when you add those together. Now let me pause right here, because for better or worse, the author of the lab manual has used some older notation for grams. And so I just want to address that. The G and the M together is an old notation for grams. And so in today's world, it should just be a G. So I'll just go ahead and put G for grams and just kind of cross that out. But when you see that in the lab manual, you'll understand that it means grams. The little slash does not mean divide. The little slash just is, this is telling us that we have a vector. Remember, a vector has a magnitude and a direction. And so our goal here is to find out what do these two add up to be. And we're going to do that two ways. The first way is making the drawing itself. That's why you need the graph paper and the protractor. And as you saw in the lecture, and you'll keep seeing day after day, to get you to understand the physics, I'll do a lot of drawings. And I'll do a lot of these arrowheads. And this is a way of actually doing them. And then what we'll do is we will actually apply these forces to an actual object. You can't see it because it's off camera, but when I'm done here, I'll walk over just to the side here of the camera and actually use the equipment to show you, because here's the lab. The lab is hopefully this, that if you combine these two forces to get the net force, and you do it with a drawing, we want to convince you that the result you get from a drawing is identical to the real world, and that's why we'll actually then do the experiment. So on camera here, I'm going to let you do most of the drawing. I'll do a rough sketch to kind of get you going, and then I'll actually do the experiment. And what I'm going to ask of you is that you do the rough drawing first. In other words, you make a prediction of, if you put these two forces together, what should you get? And then I, or we together, will actually do this experiment on what we call a force table. We'll actually combine these two forces together and see what they come out to be. And then hopefully by the end of it, you'll learn quite a thing about vectors. You'll learn, number one, that, hey, these drawings do match the real world. That's the good thing about it. And the other thing is you'll begin to realize that the net force is very dependent on direction. Not just on the number, but also on the direction. And that's the big thing that I'm emphasizing all day long. I emphasized it in lecture, and I'm emphasizing it here, that some physical quantities, and the four we've done, position, velocity, acceleration, and force, matter on their direction. Whereas other things, the direction doesn't matter, as you heard me mention in the lecture. What did I mention in the lecture? Time, temperature, and mass. And there are other things. So there are other vectors and other scalars, but we'll get to that as time goes along here. And so here is going to be step one. Step one is to make a drawing. And so let me kind of demonstrate a rough drawing, and then I will ask you to hit pause and then actually do your first drawing. And so if you can imagine up here, I have my first graph paper, and right in the middle I will make then the grid, the X and Y grid. This is my graph paper. Now I'll set that down. But to represent in a drawing this first force, let's give it its magnitude and its direction. And so if you read the introduction here, your author suggests this. Your author says, in your drawing, make a distance, I'll put it over here, what we call the scale. Draw a line 1 centimeter long to represent 10 grams. So that would mean here, for this first force, 100 grams needs to be a line that is 10 centimeters long. Okay? So that's going to be our scale. So to represent the magnitude of the force, we will represent that by how long the line is. See, because again, we're actually drawing position vectors, the distance. But again, we want them to represent the force vector. But they are really one and the same. And that's the idea here. Okay, the other part of this is not only its magnitude, but its direction. And so that's 0 degrees. And if it's been a while since you've used a protractor, let me just kind of put, here's a protractor. And if you remember, 0 degrees is straight along the x-axis. 90 degrees is straight up. 180 degrees is in the reverse direction, or negative x direction. 270 is here. And then 360 is also 0. Now, one of the ones I know students have challenges with is number 3 here. And so let me point out that 290 degrees is actually the same as negative 70 degrees, okay? So we could go positive or negative. So clockwise is negative, counterclockwise is positive, okay? Another angle to point out, not usually a hard one for students, is 120, and that's what we're going to do right away. And I think that's the only two I really need to point out. Oh, 220. I should do 220. So 220 would be about here. 220. It would be 40 beyond that. And so that's where 220 is. All right, so there's kind of a little review of the angles around a circle. But here's the drawing that you need to do first. You need to take your ruler. And as I said, to represent, maybe I'll change colors here. Maybe I'll go to a red one so it'll stand out. But I would do this. And try to do this accurate. That's why the graph paper and the protractor are kind of important. And again, if you don't have the best quality protractor because you printed it, it'll still work here. But take some time here. I'm going to just kind of hand sketch it, so mine will be less than perfect. But the better you can get this, the more impressed you will be with your results here. All right. So again, to represent this first force, I would do this. I would make a line that is 10 centimeters long. Maybe I'll even put an arrowhead on it to kind of show that, okay, this is the direction of that force. And notice then the 0 degrees is right along the x-axis. So I've got my first one right there. Okay? Now, what do I do with the second one? Well, remember, we're trying to combine them together. And so just like if I was walking, I would say go on a little hike and do this. When you get done with that little hike, do another little hike, okay? What's the result of those two? So you would look all the way back to from the very beginning to where you finished. My point is this, that in order to combine two vectors together, you would then make the first motion, and wherever that one ended, you would then do the second motion. Okay, so when I go to draw the second one, I do the drawing of my second one where the first one ended, right? And the total result from the beginning of the first to the end of the second is the result of those two. Watch. So the second one says, make a second force that has the same magnitude. Okay, so same magnitude. So that means on my drawing, it's going to be 10 centimeters long. So here's my red. Here. And it says draw it at 120 degrees. All right, so grabbing my protractor, and I'll say it again, you draw the second one where the first one left off. And so I'll put my protractor here. And I'll look for 120 degrees. So there's 90, 100, 110, 120 right there. And if I draw 10 centimeters long, I would say now I have just combined the two forces. And I'll say it again, because you need to do this 5 times. You draw the second one where the first one left off. You start the second one where the first one left off. So you have the first plus the second. And then the result is the two combined. That is, from where the first one started to where the second one ended. So if you'll let me change colors again here, this would be my result. My result would be, where did the first one begin? Right here. Where did it end? Right here. And to try to get something accurate, let me draw it with a straight edge. Okay. So that's the result of those two red ones. And so what you're asked to do, let me hold up the graph paper here, is you're asked to make that drawing first, and then right here, where it says graphical results, it says write down the magnitude and the direction of what those two are equal to. Okay, so looking at my graph, and maybe I will put over here and then over here. So this is the graphical results, or what we call the resultant. And so I'm going to use my graph here, and I guess the first thing I will do is get its magnitude. Okay, so how long is it? So I'm going to come over here. I'm going to measure how long it is. And mine looks like it is a little over 10 centimeters. Not much. I will tell you, if I have drawn things perfect, it would come at exactly 10. But hopefully with your graph paper, you'll get things a little more accurate and close to 10. But I'm close enough that what I could say is, because I had 10.2, and 10.2 would say that this is 102 grams. And so what I'm saying is, if I put those two forces together, which would be 100 and 100, but remember, it's 100 at 0 degrees and 100 at 120 degrees. If I put those two forces together, what do I get? And what I'm saying is I would get a force of basically 100, or at least close to that, 102. And what direction would it be? And that's where the protractor comes into play. And so I would lay out the protractor and say, okay, what angle is that? And it looks like that is 60 degrees. Okay, so I'm going to write on my piece of paper 60 degrees. And so what this drawing is predicting, this drawing is predicting that if you took those two forces, okay, force 1 and force 2, both of a magnitude of 100, one of them at 0 degrees, one at another angle of 120 degrees, and you put them together, the total result, what we called the net force in the lecture, because that's what we need to get the acceleration, the net force would have a magnitude of 100 and an angle of 60 degrees. And I always find that interesting, because really you're saying you put 100 and 100 together, you get 100. And that just sounds funny. But it also illustrates direction, because if you look here, 4 of these 5, the magnitude is each 100. And so when we put 100 and 100 together, sometimes we will get 100, sometimes we will get 141, sometimes we will get, but just depends how we put it together. And this is going to illustrate how direction comes into play. It's not just the magnitude. All right, so as I said, this would be a good place, you know, to hit your space bar and say, okay, I'm going to stop now and do my drawing. All right, so do that now and do your drawing and hopefully get your prediction. Because once you're done, start it again. All right, so we're back here. So you undid the space bar. Let's do the second part of this experiment. And that's with the force table. So let me come over to here. And this is the part that I'll be the partner with you. So you're going to do the drawings. If this was face-to-face, I would say have one of your partners do the drawings and the other one kind of hook it up. So since I'm here in the lab, I'm gonna be hooking it up here. But as you can see on the video, I've got this protractor and I've got this string tied to it. And I'm going to start with just making one string completely loose. Okay? I'm going to use this one to figure out what is the sum of these two. Okay? And so if you remember the problem we just did, the problem we just did says apply 2 forces, 100 grams and 100 grams. The first one was at an angle of 0 and the second one is 120. And you can see that I have put this pulley already at 0 degrees and the second pulley is at, or close to, let me do a little bit better, 120 degrees. Now, down here under this hanger, I have some weight. And this weight by itself is already 50 grams. So I'm going to reach down in here and grab a 50. No, I'm not. I didn't grab the 50s. So I'll tell you what, I'm going to grab a 20. And another 20. And a 10. Okay, so that is 100. And to get you an idea of the equipment, I am now then pulling on this little ring with a force of 100 grams at an angle of 120 degrees. And so, actually, I wonder, does this look funny on the video? This is kind of backwards. I wonder if I should, I tell you what, I'm going to do this. Just to, maybe so it'll maybe look better on the video. Because this is how you'd be looking at it over there. Okay? So your 0 would be off to this side, and 120 would be right there. So I'll use the inner circle here. So this is a positive, this is 120. So I'm going to put this over here at 120. So let me just leave that one loose. Okay, so I have 120. That's one of the forces. That's the second one. The first one, I don't think I got the number right. I got the angle right at 0. So yeah, so this is just 50. So let me grab a 20 and a 20 and another 10 and hook that one. There we go. All right. So again, this is saying, or what I've just hooked up are the 2 forces. I've got these 2 forces on this ring. Again, the first one, 100 grams at 0 degrees, and the second one, 100 grams at 120 degrees. What does it add up to be? And I'm hoping even on the video you can kind of see this little peg right there. You can kind of see this ring is getting shot out at that angle right there. And if I, removed this peg like that, and let go, and I better not, it goes shooting off. And that would tell me the direction that those 2 are equivalent to. It wouldn't tell me the number, but at least it would tell me the direction. So here's what I'm going to do. In order to figure out what those 2 add up to, I'm going to find what we call the equilibrium. What is the same magnitude but opposite? In other words, what do I have to put over here in order to balance it? Because this is poling opposite of the resultant. And so the equilibriant, as the name implies, is what force is needed to keep it in equilibrium. And that means this equilibriant would be equal in magnitude, but opposite in direction of what these two add up to. And so remember, when we did the drawing made the prediction. In fact, to shoot the camera back up here, it may have been a while, it took you a while, you hit the space bar, and it took you a while to do the drawing. But when I did the rough drawing on the board, I came up with a prediction of about 100 grams at an angle of 60 degrees. So the goal here is let's take this prediction and see if it matches up here. Or at least let's see if we get the same thing. So coming back over to here. The prediction is that the resultant would be 60 degrees. All right, so in this direction. Now exactly opposite of that, the equilibrium, is what you get if you then either add or subtract 180 degrees. So if I have 60 and I go a full circle, I add 180. So 60 plus 180 is right here, 240. So that prediction is that pulling in this direction of 240 should bring this into equilibrium. And that's where this pulley is. And it also is predicting that I would have to hang a force of about 100 grams. So let's see if that works out well. All right, so 50, and that 20 makes 70. Another 20 makes 90, and a 10 makes 100. And I suppose for accuracy I should do 102, but to be honest, my drawing is so bad. But we do have some ones, little pieces of plastic we cut to make 1 gram. So that'd be 102. And so let's just see if this brings it into equilibrium. And sure enough, I could safely remove the peg that is keeping it from flying off. And so I would say, yes, these two forces add up to the opposite of this equilibriant. And so what I'm going to write down here is my equilibriant. And so on my graph paper, or on my lab paper, you will see that it says here, when you actually do the experiment, and so it says, what is your experimental equilibriant? You will hopefully find that running the experiment and drawing the pictures give you the same thing. And other than the 180 degrees, I should emphasize that. So I'm just going to write down the equilibrium. So looks like I got it to be equalized at 102 grams, good, at an angle of 240 degrees, good. Because that is saying that this is the force that equalizes this. And this is the force that these two add up to. Okay? And so that's your first experiment. Now, let me help you with the other ones. So the second one's going to look like this. So let me grab my eraser here. Let me leave my graph paper up here. Let me clear off these two forces. Let me clear off the results of that one. And we'll just do the same thing a second time. And again, you're asked to do this 5 times. So looking at this, it says that the two forces are this. The first one is 100 grams at 0 degrees. In fact, I'll pause right there. I probably shouldn't have erased it. Every one of these 5 always is 100 grams at 0 degrees. So I might as well just leave that on the board. And on my force table, I just will say, hey, I'm not going to touch that one. What keeps changing is the second one. So you can kind of learn the idea that direction is important because 4 of these 5 are all also still 100. They just give you different direction. Now there is one where they change the magnitude, so you can get a feel for that one too. That's the 4th one. But the second one then has an angle of 60 degrees. And so you're going to do the drawing. Let me give you a rough sketch of the drawing, because in a minute I'm going to ask you to hit the space bar and then do your prediction, do your drawing. Okay. I will say that you might want to put your grid a little bit on this side of the graph paper, because it does get a little longer this direction. Because watch what happens. I'll just do a rough hand sketch and get my red one out, because the first one would be just like before. I would draw it 10 centimeters long at an angle of 0 degrees. And the second one, and it's probably worth emphasizing, draw the second one. Start the second one where the first one ended, because we're trying to see the results of these two. We call this the head-to-tail method. We do the first one, and wherever this ends, then we do the second one. And if we draw them head to tail, this is really a way of saying, okay, this is the combination. This is the result of the two. Okay, so my second force is 100 grams, so I'm still going to draw a line that's 10 centimeters long. But this time I'm drawing it at 60 degrees instead of 120. And so putting my protractor up here and going to 60 degrees, right about there. And I won't do mine very accurate here. I'll just kind of hand